Hello and welcome to this R tutorial. So in the previous tutorial we imported the dataset, and today in this tutorial we're going to implement the UCB upper confidence bound algorithm. So I'm not sure if it's bad news or good news, but there is actually no package that we can use easily to implement this UCB algorithm. So that's the bad news, but the good news is that we are going to implement the UCB from scratch. And that's good news because that will give you the opportunity to really improve your skills in R. So be ready. It's not going to take 3 or 4 lines like we used to have before. We are going to implement the whole algorithm from scratch without using any package. And we're going to do it step by step. And speaking of steps, let's now actually jump to the slide of the upper confidence bound algorithm. So this algorithm takes 3 steps. The first step is, at each round n, we consider 2 numbers for each add I, that is for each version of the add. These 2 numbers are ni, the number of times the add I was selected up to round n, and the sum of rewards of the add version I up to round n. Okay, so the first thing that we need to do here is to declare these 2 variables because we will need them afterwards. Okay, so the first one, the number of times the add I was selected up to round n. Let's actually call this variable numbers of selections. All right. So we need to consider this number for each add I. So what we're going to do is create a vector that will contain each of those numbers of selections of each add I. So we will set this variable equal to a vector of size d, and we will initialize all the d components of this vector to 0. And so how can we do that in R? Well, we simply need to type integer and in parentheses d. And this will create a vector of size d containing only zeros. And we are doing this because, of course, at the first round, each version of the add hasn't been selected yet, so the number of times each version of the add was selected is, of course, 0. Okay, so done for the first number. All right, and the second number is the sum of rewards of the add I up to round n. Okay, so let's call this variable sums of rewards this way, and same, we need to take the sums of rewards of each version of the add at each round n. So we're going to set it as a vector of d components as well, exactly like we did for numbers of selections, and same, we will initialize it to 0 because, of course, at the first round the sums of rewards of each version of the add is, of course, 0. So we will just copy this, copy, and paste it here. All right, so basically step 1 done. Now let's move on to step 2. Step 2 is, from these 2 numbers we compute first the average reward of add I up to round n, and second the confidence interval at round n. So basically we need to compute these 2 numbers but at each round n. So let's implement this step 2. Since we need to compute these 2 numbers at each round n, of course what we need to do is to make a for loop. Alright, so that's what we're going to do. We're going to go through all the rounds from 0 to the 10,000th round. So for each round n, so we're calling the rounds n, so now we need to input the lower bound, which is 1, so that's the first round, and then the upper bound, which is n. So n is the total number of rounds, that is 10,000 rounds. So in case you have a problem with more rounds or more users, we will, declare this variable here, n equals, well, here for our problem, it's 10,000. All right, 10,000. So right now we're in the loop. And so what do we need to do? We need to compute for each version of the add the average reward and the confidence interval. So that's exactly what we're going to do. And since we're doing it for each version of the add I, well, what we need to do now is again another for loop. And this time we're going to loop over all the 10 different versions of the add. So the adds are indexed by I, so for I here, in 1, and then again we're going to input here D in case you have more versions of your add or more arms for your specific problem. So we are going to declare a new variable here, which is D, and since it's the number of adds, we will set it equal to 10. All right. And now we're entering into the second loop. So right now at this level, we are at a specific round and dealing with a specific version of the add. And now we can compute our two numbers, the average reward of the add I and the confidence interval. So let's start with the first number. The first number is the average reward. So let's call it average reward and equals. All right, so what does it say? It says that it's the sum of rewards of the add version I up to round n divided by the number of times this add version I was selected up to round n. So simply let's write this formula. We already have these two variables. Well, we have the vectors, but of course we will take the ith element of these two vectors because they correspond to our add version I of the add. So let's do it. Sums of rewards, and we take the ith element of this vector divided by numbers of selections, and same, we're taking the ith element of this vector. Great, so we have our first number computed, the average reward. Now let's take care of the second number, the confidence interval. Well, we will not build the whole confidence interval. What we will compute right now is the upper bound of the confidence interval because that's what we need for step 3. As you can see, step 3 is we select the add that has the maximum upper confidence bound. So we just need the upper confidence bound of this confidence interval. And so what is this upper confidence bound? Well, it's the average reward plus delta I of n. And delta I of n is given by this formula. It's the square root of 1.5 log n divided by NIN, which is the number of times the add version I was selected up to round n. So let's compute this delta first, and then we'll compute the upper confidence bound. So delta, we'll call it actually delta underscore I, and so it's equal to square root, which I call SQRT, parenthesis here. Okay, so what do we have first? We have this 3 divided by 2, then times, and then we take the log, so log here, of n, that we divide by the numbers of selections of the add version I. That is the number of times the add version I was selected up to round n. Okay, so great for delta. Delta is ready, and therefore now we are ready to compute the upper confidence bound, which is all the essence of this UCB algorithm. So let's do it. Let's compute the UCB and let's call it upper bound. This way, upper bound equals average reward plus delta I, exactly like in the slide. Okay, so great. We just computed the average reward and the upper bound. And therefore, we are done with step 2. So now let's move on to step 3. Step 3 is to select the add version I, that has the maximum upper bound. So now things get a little more complicated because we need to actually create a vector, a huge vector, like a huge list that will contain the different versions of the add that were selected at each round. So let's do this. We're going to declare here a new variable that we're going to call adds underscore selected. And this variable is going to be the huge vector that will give us the list of all the different versions of the add that are selected at each round. That is, at the end of the algorithm when we run it, the add selected will be a vector of 10,000 elements, and each of these elements will be the add that was selected at each round. So we will clearly see the results of the strategy used by the algorithm. Okay, so as usual, we need to initialize this, and we are simply going to initialize it as an empty vector, because what we'll do next is to append the different adds one by one up to the last round, round 10,000. Okay, so now the question is, how are we going to append the different versions of the add in this add selected vector? Well, let's go back to the slide. Step 3 is we select the add I that has the maximum upper confidence bound. So we already computed the upper confidence bound, and now we need to create another variable that will be the highest upper confidence bound, because right now this upper bound variable here is just the upper bound for each of the d versions of the add at round n. And so that's why we need to create another variable that will take the maximum of these upper bounds here of the 10 adds at round n. So let's create this new variable, and we're going to call it max upper bound. So since this max upper bound variable is going to be different at each round, well, we need to initialize it at each new round. So therefore, this variable max upper bound will be initialized right here. So we will initialize this max upper bound variable here to 0. And then what happens is that we will compute the different upper bounds of each of the 10 adds, and then we will compare these upper bounds to this max upper bound. And each time the upper bound of the add I here will be higher than max upper bound, then we will set max upper bound equals to upper bound. So that's the idea. So let's do that right now. So basically what we have to do here is, in this for loop, we need to add a new if condition. And this condition will be if upper bound larger than max upper bound. And then what happens? If upper bound is larger than max upper bound, then we need to set max upper bound equal to upper bound. This way, you know what will happen is that we will compute the different upper bounds of each of the 10 adds at round n. At first, this max upper bound is equal to 0. Then we compute the first upper bound, and of course it will be larger than max upper bound because it's equal to 0. So then max upper bound will be equal to upper bound. So that's for the first add. And then we will compute the other upper bounds of the other adds. And each time we find an upper bound that is larger than max upper bound, then max upper bound will be equal to this new upper bound. All right. So this way, we will get the maximum of the different upper bounds of the 10 adds at the specific round n. Alright, and now we need to do one more thing. We need to select the add that has the highest upper bound, and therefore each time we find this upper bound being larger than the max upper bound, not only we need to do this to keep the max upper bound, but also we need to keep track of the index that has the max upper bound. And to keep track of this index, what we need to do here is to create a new variable here, which we'll call add, and we will make it equal to I, because right now we are dealing with a specific add, because we are at a specific I of this for I loop here, and so I here has a specific value that corresponds to a specific add, and so we need to keep track of this specific add each time we find an upper bound that is larger than the max upper bound to become this new max upper bound. Alright, so that's great, but when we use a new variable here, it's always important to initialize it. So that's what we'll do right now. We will initialize this add variable. We will initialize it to 0. Okay, so we're getting close. Now what we need to do is deal with the initial conditions, because this is what happens at round n. This is the strategy that happens at round n, but this is actually not what happens at the beginning, because at the beginning, during the 10 first rounds, we don't have much information of the adds. We don't have much information about their reward, whether they earned reward equals 1 or reward equals 0 when we selected them, because simply we haven't selected them yet. So that's why we need to deal with the initial conditions, that is, choose which adds we will select during the 10 first rounds. And so according to you, what will be the strategy to select the ads during the 10 first rounds, given the fact that we don't have any information? Well, there is actually no strategy. We will simply select the 10 first ads without using the strategy here. We will use this strategy as soon as we have some information of the reward of each of the 10 ads. So basically what we'll do during the first 10 rounds is to simply select the 10 first ads. That is, round 1, we'll select ad 1. Round 2, we'll select ad 2. Round 3, we'll select ad 3. Up to round 10, we'll select ad 10. And then that will give us some information about, the number of selections of each of the 10 ads. Well, at round 11, the number of selections will be 1 for each of the 10 ads. And we'll also get some information about the sums of rewards. The sums of rewards will contain either zeros corresponding to the ads that got a 0 reward when they were selected during the first 10 rounds, or ones corresponding to the ads that got a 1 reward when they were selected during the first 10 rounds. So let's do it now. Let's simply select ad 1, ad 2, ad 3 up to ad 10 during the first 10 rounds, and then let's use the strategy. So to do this, we will add an if condition here, which will be if numbers of selections I is larger than 0. So that means if the ad version I was selected at least once, then we will use this strategy. And actually, we need to align this. And so now, thanks to this condition here, this strategy will be applied after the 10 first rounds. Okay? And now we just need to add a little something to make sure that the algorithm selects ad 1, ad 2, ad 3 up to ad 10 during the 10 first rounds. And to do this, the trick is to add an else here, else, and then we will set the upper bound to a very large value, like 10 at the power of 400. So to get this, we can use 1 E400, and that's 10 at the power of 400. So now I'd like to give you a little enigma. I would like you to figure out why we're using this very large value 10 at the power of 400 for the upper bound here in this else condition. Try to figure out why, try to figure out how it will be useful for what we want, and I'll give you the answer and the explanation in the next tutorial.